in transactions. So there are other papers like that of Michael Lau, which appeared in Pacific Journal.
So these are both recent?
Yeah, everything is within the last 3-4 years.
Oh, I see.
That might be, yeah. So this is Michael Lau that appeared in PJM. Yeah, so that was for the loop modules kind of thing, the classification of integrable representations. Okay. So that's, yeah, so there are the original papers there.
So when you say these are the more recent references,
so these are all about finite dimensional representations of G1030.
oh, including your thing.
Exactly.
Oh, I see.
Yeah.
Okay.
Arbitrary
Yeah.
map algebra.
Of current algebras and G tensor array. Okay.
Yeah.
Map algebras. Okay. So map from an affine variety X to with values in G.
That's right. And Nair and Savage do also the twisted case, so the equivalent case.
Okay. Current algebra, more generally. Map algebra. Or more generally map algebras. So that's and then twisted. So this is what by twisted case you mean the equivariant map algebra?
That's right, yeah. And this is about irreducible finite dimensional representations.
Okay. So irreps of, so classifying finite dimensional irreps of.
Yeah.
Huh. Doing special cases. Okay.
And Michael Lau is again.
He's also special. But he takes, I mean, he's the one who discovered this useful result of Hubbard. So these Garland formulas, for instance, which I think are very useful, and Garland's original paper is a bit hard to, but what one usually needs are reformulations, which you can find in this paper on wild modules that I'm doing now. Wild modules for classical functional analysis. But anyway, that will be a reference for wild modules too.
Garland's formulas, Garland, of course, it says this is Garland's original paper.
Yeah, Journal of Algebra, 1978. And then there's this paper on the archives now, which is by Sam Chamberlain, where he totally generalizes Garland's formulas for G1030. And it's even more general than Garland.
Did I get that?
Chamber, yeah, Lin, L-I-N.
Archive,
Yeah,
recent,
yeah, in the last few months.
and generalizes.
Garland for loop algebras and for G1030.
What do you mean by generalizes for loop algebra?
So Garland tells you how to move, let's say, y tensor t past x or x past y tensor t. Or what is the general term in your loop algebra that you want to deal with? You want to deal with something like y tensor t power r1, y tensor t power r2, and you want to move it past x tensor t power s1, x tensor t power s2. Yeah, so I mean, sometimes it's a bit of a nuisance when you only have these two, because then you don't have as much control as you would like. So, but he just,
So it
it,
doesn't arbitrary.
yeah.
But
I mean, it's
not.
occasionally a nightmare, but it's useful. I think. So,
Not for the equivariant map algebra.
he doesn't do it for the equivalent map algebra. So I was going to say, so for the twisted algebras, there is this thing called, there's a guy called Mitzman, M-I-T-Z-M-A-N, and I think his appears in the memoirs. And I guess it goes back sometime in the 80s.
Members of the AMS, huh?
Yeah. And he does Garland type formulas for both twisted and untwisted affine algebras.
Uh-huh.
So he has a different, more generating series formulation. And in this same wild modules paper, no, we had another paper. So we generalized Garland's formulas to the quantum case.
But let me, since I don't want to miss that, you said something about your paper being a reference for while modules also. So which one is this?
So let me tell you about this one, because this is related to Garland's formula.
Yeah, okay.
So I think it's called Quantum Affine Algebras and Roots of Unity. That appeared in representation theory in the 90s, 97. I don't know.
Was it journal existing then? It was, okay.
Now, by now, yeah.
Okay.
Yeah, I think it was 97. So in that paper, we do Garland's formulas in the quantum case. And we give a very different proof as well. So if you take that paper and put Q equal to 1, then everything.
We can improve both parameters.
Yeah. So just put, so also I think the formula in those papers are written in a way that's more adapted to what we study. You see, because what Garland is interested in is moving Chevalier generators past each other. So he has to move X past YT or something, whereas, so you always get into these problems with signs and how to adjust them very slightly. So I think in our paper we just do it in the context that we need it. Right. So anyway, so it has that. And then there is a paper by, there's a paper by Akasaka. He's a student of Kashiwara. I think it appeared in RIMS. Publications of RIMS.
So this is also related to the Garland?
So he proved a Garland type formula for quantum A22.
Twisted.
That is the only case in the twisted case which is important. That's important, yeah. All the other cases are sort of similar to untwisted, but this is intrinsically different. So for A22. Yeah, so Garland's formulas are used mainly to define Z-forms for affine algebras or quantum affine algebras. I mean, that was the motivation, right? So once you define Z-forms, then you want to go to characteristic P, for instance. That's one thing. But actually, there isn't very much literature on that. So So Garland proves the following. He constructed a Z form, and he also showed that you have a Z lattice in the positive level representations. Okay. So then it's immediate. So then really what you should do is you should reduce mod P and ask yourself what you get. And you can do the same thing. So what we did was we showed you had a Z form or ZQQ inverse form for quantum groups at roots of unity. And again, you want to reduce to roots of unity. So that whole thing has not been studied at all in the literature. So, so the modular representation theory of these positive level representations. There's only one paper.
Hmm? You're not talking about, you're not, by positive level representations, then
Kac-Moody.
Right?
Yeah.
You're not doing your level 0.
No.
No. So, but even that's completely unknown.
Yeah, so the only thing so for roots of unity, I wrote a paper with Jing, which showed that if you take the level 1 basic representation, then it stays irreducible in the quantum case when you go to a root of unity. But that's the only result of that kind. So nobody has actually gone to characteristic P. Actually, I think you should write mod P / roots of unity, because what we actually do is roots of unity. But UQ, yeah.
For example, the analogous question for just the basic representation of an affine, if you reduce modulo P, then does it remain
irreducible? Yeah. So the proof that we gave for roots of unity, the exact same proof goes over with, to, yeah. I mean, so, when you're doing roots of unity, you need somehow the root of unity to be sufficiently big or something, and it's the same sort of condition. But nothing is known about what happens for another level representation, or, and I think the methods we use won't work, but because it depends on how it's realized. But, yeah.
But is this only for ADE, for example, or is it?
I don't know.
Depending on how it's realized, then unless some.
But then I think maybe it's only ADE. I could be wrong. I just don't remember. So that appeared in Duke, and that was also in the 90s sometime, I think. Yeah. 90s or early 2000s. Yeah, but as I said, that's the only thing that's known. It would be nice to have some kind of result like Anderson and people have, right, in characteristic P, that at least it remains irreducible if you're in some alcove and some things like that. So, but I guess since characteristic P is already bad enough for simple algebras, nobody really pushes it further.
There are two ways in which this fails to be semi-simple. One is because of the affine, and then also the characteristic.
No, but this will be But when you're working with these positive level representations, those are semi-simple.
Those are semi-simple.
But so again, Mura and Yakelich do also study these things for finite dimensional representation. So then again, as you point out, it is doubly non-semi-simple. Yakelich, Jakelic. Mura was also there, yeah. They were both, yeah. They both gave talks. Diana, yeah. So they have, I don't know, 2 or 3 papers on both mod P and roots of unity for finite dimensional representations. It's on the, I mean, their papers have all appeared, but I don't offhand remember where. So, but they're all on the archives, and they're all within the last 5 years. So,
This is the quantum affine.
quantum and classical affine, yeah. I mean, mod P will be classical, quantum affine will be bits of unity.
So this will be finite dimensional representations of the current algebra or the loop algebra?
Loop. So Vishwanath needs to prompt me now. I don't know which lecture we're on to.
So then there is a Z form even for these finite dimensional representations.
Yeah. You can just use Garland. Garland defines a Z form for the loop algebra, universal enveloping algebra of the loop algebra. Oh yeah, so you have to do some work. Yeah. Yeah, so in characteristic P, yeah, they have to do some work because there aren't, you have your polynomials, there aren't very many of them. Yeah, but there is something, yeah, I don't remember. But yeah, they develop all this notion of while modules and things like that.
Okay, so I guess next lecture.
No, just one second. You said something about your paper with cascading.
Oh.
While module, something.
Yeah, this one, yeah, so
Yeah, no, that's what's coming up next.
that'll come up next anyway, so I think, yeah.
Fine.
So.
So I guess lecture 4 was quantum of again. So I think firstly this we talked about this loop-like presentation.
I think for that probably the best reference is this survey article that I wrote with Hernandez. We have a very long list of references in there. And also so also for references, I produced a very long list of references for my lecture notes, which I gave in Canada. So both are sort of, since both David and I are quite algebraic, both are sort of algebraic references. So we have only one paper, so.
And it's on the archive.
Yeah, it's on the archive. Yeah. And these are the Ottawa Summer School lecture notes. So they both have tons of. So the Hernandez paper with Hernandez will be quantum, and the other will be classical. So blah, blah.
This is quantum. This is also from the same school, or?
No, this is some proceed. That appeared, yeah, that's on the web, and that appeared in Contemporary Maths, and then I don't know what this is. Yeah. And then the other one is in this. And I guess Prasad also, Senesi wrote some survey, right? On loop modules he wrote a survey which might, and block decomposition and so on. So there's a survey by Senesi. Which might actually be in the same, yeah, I think it's in the same Contemporary Math. Okay. Yeah. Anyway, it's on the web.
And it's regarding what?
So he talks about loop modules rather than just finite dimensional, is that right?
The integrable.
Yeah. And also in the twisted case, and also block decompositions.
And this
Yeah.
is all for the loop algebra.
It's all for the loop algebra. Yeah.
ಯಾರು ಬೇಸಿಂಗ್ ಕಾಳೋ ಅವೆಲ್ಲ ಫೋಕಸ್ ಮಾಡೋದು
Keeping him busy, yeah.
It might look like this voice-over kind of thing.
Very ghostly. Bit like a horror movie. Okay.
So the thing you said about those Garland, those PIUs giving like group-like elements under that co-product, or even the definition of the co-product, or for more basic things about quantum groups, is there a good place?
I think this quantum affine algebra at roots of unity has a lot of this stuff in it. And there was the original paper so SL2, for instance, there was an original paper we wrote on I think it was just called quantum affine algebras. It appeared in CMP in 1990. No, they don't have co-multiplications and co-products and so on. Not for Drinfeld generators. They don't care about Drinfeld generators.
Co-product. If you take those Garland type elements, PIUs, they behave like group-like, but up to some first order.
Yeah. So I think that is really in this this paper, Roots of Unity. And then it's also this relation to canonical basis and so on was made in this paper which we wrote jointly with Beck. Yeah, so some of it is there. The other one is in this quantum affine algebras where the PIRs were sort of, although they were defined earlier, I think we understood them better only later. So I think in that one and, yeah, that one. Mm-hmm. Yeah, I think that is the best reference, Beck, Cherry, Presley, and that appeared in Duke.
That's reference for specifically what?
Yeah, so the PIRs are defined in two different ways. So as I said, Andrew and I defined PIRs adapted to finite dimensional representations, and in that we did it defined in the same way as Garland. Then we proved that U, Q, N plus has that you have a nice lattice like you do. So we proved a Poincare-Birkhoff with Z basis for the quantum affine algebra, for the positive part of it. And then we related it to the canonical basis and showed that the Schur functions appear as the canonical basis. So they're part of the global crystal basis. Oh, thank you.
Theorem about Dirichlet polynomials and so on. You quoted reference very precisely 90 and 94.
Yeah, that we wrote so 1990 was only about SL2, and then in 1994, I think that appeared in some Canadian Math Society proceedings. I mean, Math Reviews will have it, so I don't. And that was called I don't know what it was called.
So this one here, this paper, and 1994.
That appeared in some proceedings of the Canadian Math Society meeting, I think. In Banff. There was a conference in Banff that year. Yeah, so see, 1990 was only SL2.
Okay, 94 was the general.
Was to classes show that irreducible representations are given by the Drinfeld polynomials. Yeah.
And you are the ones who called it the Drinfeld polynomial. Okay. It appeared.
Drinfeld had announced a classification for the Yangians. So at that point, I think we wrote a paper on the Yangians, and so we called that the Drinfeld polynomials then, and then it was very similar in the quantum case. So then the name kind of stuck.
So Drinfeld announced, what did he say? He announced a classification of
Representations of Yangians, so irreducible finite dimensional representations of Yangians.
Okay, and those involve those.
Yeah, so those are also given by polynomials.
Okay.
So the Yangians, so I'll tell you what, a Yangian is, so that's another interesting, so the Yangian is a deformation of the current algebra. And the general rule is that anything you can prove for the Yangian, you can prove for the quantum affine and vice versa. But that's a general principle.
Can I write it?
Yeah. It's kind of folklore. It's not a general principle. It's folklore that anything you can prove for a Yangian, you can prove for quantum affine.
Also for the quantum affine. That just means that when you deform, you could just deform the current and worry about it and do it, and then hopefully.
It's not a very precise statement, but it.
Yeah, I understand. But so
Yeah.
if you can try it there if you.
Yeah, if you understand things correctly, then you can. What you can do for the Yangian, you can do for the quantum affine, and so.
Sorry, does it remain true as, I mean, when you put Q equals 1, is it also sort of true that what you can prove for the current algebra somehow can be made to work for the.
That's what you would hope. So the point is, so the current algebra is, I mean, the Yangian is just harder to work with than many of the results remain true. I mean, you have these PIs and you have all kinds of things. But somehow at some stage we stopped working with the Yangian and switched to quantum affine. Part of the reason is that Lustig was busy proving all these very impressive results for the quantum affine. And so he made all this business about Z-forms, how to produce lattices. But for instance, so the Yangian is an algebra which is actually first defined over a power series in H, over the ring of power series in H, and then you actually specialize H to be 1, and then it's defined over the complex numbers. Okay. So for the Yangian, one doesn't know a Z-form, for instance. And then if you don't know a Z-form, you can't reduce mod P and so on. So it's always been a bit of a thing that you do everything for UQG and then you're not motivated to do it for the Yangian, so you don't know if things are actually different. But
Does this general principle also go the other way?
yeah, both ways. That's a belief. And so basically any theorem, belief is that any theorem you can prove for the quantum affine, you should be able to prove in the other cases. But belief is slightly different from actually proving
I
it.
understand. It's a general-
Yeah. And then,
general guideline.
right, and people have always claimed that there are such equivalences, but now I think there is this paper of Toledano and Sachin Gautam, whom you know, where they actually give some rigorous functor or some rigorous way to produce, I don't know which way it goes, I think from the quantum affine to produce representations of the Yangian. So their paper's on the web. I don't remember the name. So it's Gautam and Toledano.
Did you say that the Yangian does not, it's not known if it has a Z form?
Yeah, it's not known.
But it's possible that it does.
Yeah.
I don't get the name.
Toledano, T-O-L-E, his advisor, D-A-N-O.
Toledano, and isn't it a double name? Toledano.
Valor, no, is it?
Laredo.
It's, God, what is his name? I've forgotten now.
Starts with a V.
Yeah.
Valerio-
Valerio Laredo Toledano. Is it Toledano? Okay. Somehow everybody knows him as Toledano.
Okay.
So they give
You
you,
know Gautam over Sachin.
that's right. So they give some functor from the category of finite dimensional representations, perhaps.
Some meaning to this.
Some meaning to this, yeah. But they don't know, but one of the problems is that they don't know how this functor that they define behaves with respect to tensor products. And tensor products play a big role in all this. So given an irreducible representation, they tell you how to maybe get an irreducible representation of the quantum affine. But supposing you take the tensor product of 2, then they don't tell you what happens over there, I think.
But it seems unknown or is unknown?
Unknown. They don't know yet. And so I asked Toledano if that result, somehow, if you can take a Z form, ZQQ inverse form for the quantum affine how does it behave under their functor? And they didn't know that either.
So functor tensor products are known, Z forms also.
Its behavior under Z forms, yeah.
Of the functors also with respect to Z.
Yeah.
So functor takes a representation of the quantum affine.
I don't know. I mean, it might actually be from the algebra to the algebra, which behaves well on representations. I just don't remember that talk, but you should have Gautam come in. Gautam was here sometime in August, right? Yeah.
He did come, we didn't go to
July.
You didn't go to his talk?
No, we
it
were.
was at the same time as the
Oh, your instructional. Oh, okay, yeah. Also with respect to Z, ZQQ, yeah, Z forms. And so I don't know how their functors behave with respect to indecomposable modules. So there isn't a theory of wild modules for the Yangian, for instance. And there isn't a theory of any kind of theory. So I don't know how their functors would behave with respect to that either.
how did these Yangians can arise in the first place?
So all these, how does any quantum thing arise? It's sort of, there's some particular bialgebra structure on the dual vector space that you're trying. So there's something called these classical Yang-Baxter equations. And then what they are somehow is to define a bialgebra structure on the dual, which is compatible with the Lie algebra structure, and then you try to deform that and you get a solution of the quantum Yang-Baxter equation. So I think very vaguely for the simple Lie algebras, the quantum Yang-Baxter equation comes without any parameters. these come from looking for rational solutions. So then you have a quantum Yang-Baxter equation which depends on some parameter u. And then you can look for rational solutions for that equation, and that somehow gives rise to the Yangians. And you can look for trigonometric solutions, and that gives rise to the quantum affine. And so that is why when you do this,
Could you just repeat the last bit?
you look for the trigonometric solutions.
No, the one before and the one before. You had 3 levels.
Yeah, so for the simple Lie algebra, your Yang-Baxter equation doesn't have parameters. Okay? But there are kinds of equations, Yang-Baxter equations, with the parameter. And when you look for solutions of that, rational solutions of that, then that comes up with the Yangians. And when you look for trigonometric solutions, that comes up with this quantum affine. And it's precisely because of these rational functions and so on that you develop poles and singularities, and they somehow correspond to points of reducibility of the tensor product. Tensor products aren't always irreducible. So in principle, they give you different kinds of solutions of this equation. And this R matrix in this context is really not very difficult. I mean, what they are, purely from a representation theoretic point of view, what they are, so if you have V tensor W and W tensor V, if you know they're isomorphic, then what the R matrix, if you take the R matrix and you compose it with the usual flip map, that's an intertwine. Yeah, the R matrix will be V tensor W to V tensor W, I think. And so then if you compose it with the flip, then you get an intertwiner for the representation. You get a map of algebras. So that's, as far as you're concerned, that's what an R matrix is, an intertwiner. So it gives you when V tensor W is isomorphic to W tensor V. So yeah, I think in one of those papers we compute R matrices, maybe in that 1990 paper, and show how you can get reducibility from.
So this loop-like presentation that you mentioned for the quantum affine, is that somehow modeled on the generators and relations for the Yangian and then generalized that way, or?
Yeah, it's just modeled on the classical thing.
It's a classical thing.
I mean, all those miraculous formulas Drinfeld wrote down without any proofs. And then I guess Beck proved it in the affine case. And Yangian's a rigorous proof was never written.
So the UPG, the definition in terms of the Chevrolet generator, that was
Drinfeld and Jimbo, yeah.
Okay, I see. Oh, okay, then that was Drinfeld and
Yeah.
Jimbo, but that predated this
Yeah.
presentation for the quantum.
That's right, yeah. But not by much. I think that was 86 and then this was 89.
Loop-like presentation for the quantum affine. So just like you had for the affine, classical affine, either in terms of Chevrolet generators, is using that matrix A, or in terms of symmetrical groups. So you mentioned you have like similar, those relations were not written. Some similar generators, those HIRs and those X plus minus IR. And then I guess we're on to Y modules.
I'm just going to use the restroom and be back. I guess, yeah. I think so, yeah. Yeah, well, there's this paper. It started as wild modules for quantum affine.
Just 1 minute. There is not enough chalk. I'll just
Okay.
some chalk.
Yeah, so that would be very nice, I think, if this could all be pushed through for those. So, yeah, so this classical and quantum affine algebras, that was the first time these were defined. That appeared in also in the 90s, or I don't know, maybe 2000, and that also in representation theory.
That's the name of the title of the paper.
So we wrote 2 papers about the same time, and one appeared in the journal Representation Theory, and the other appeared in the proceedings of one of these Durham conferences. So I don't know where. The Durham conference was in 1999, but I don't know what the series that they appear in is called. And then so I think shortly after that, Fagin and Loktev had a paper on fusion products and the Valinde formula.
Fusion products, I thought there were fusion products also for the Y module, so that was done even before the evaluation module.
No, they did. No, what they did was just fusion. I mean, they didn't know about while modules, in fact.
Yeah.
But what they just did was they defined this notion of a fusion product for graded representations. And they were interested in some conformal blocks, I don't know, something.
They started out doing the fusion product, starting with graded representations?
Yeah, of GT. So then, at some point, I guess, we discussed that they were the same thing. And so, and then Loktev and I did something for SLN plus 1. We proved their conjecture in some case, right? This while modules for SLN plus 1. While modules, Demojour modules, and fusion product, it was called.
So it was independent of the parameter. That's what.
That's right, yeah.
Sorry, once again,
Yeah.
what did you, what's the
So in Fagin, Loktev defined this thing called products, right? So families of modules coming from SLN plus 1. In particular, I mean, and that essentially that the while modules are fusion products of the fundamental representations for SLN plus 1.
So this implies one modules are.
Well, no, it's the other way. We prove that the while modules are fusion products of tensor products, fusion products of evaluation representations, fundamental.
Oh, so this is for fundamental only.
Yeah. So, so
Very Loktev is in the classical, just the classical current algebra.
yeah.
But your differential modules and so on, in that paper you do it for
Quantum as well, yeah. But what we show over there is really if you understand the classical, then you understand the quantum. That's the point.
So is there a discussion about what happens when you do this cube going to one kind of?
Yeah, it's all there in that classical and quantum affine algebras. So as I said, in those 2 papers, that's all there. Why it's enough to understand the quantum.
These two, the representation theory and the Durham conference.
I'm sorry, Vishnu, could you?
No, so the sense when you let you go into one, how that reduces to this. So, and so they've shown that if you understand the classical, you somehow enough to understand. But again, in Lockyer is a purely classical, because the fusion product is only for just the current algebra itself. There is no Q involved.
See, all this
Exactly. So around so shortly after that, Littleman and Fourier and Littleman wrote 2 papers on this.
Again on the classical case.
Yeah. They were coming from the demo. So what Littleman was doing was computing the G-module decompositions of the de Mazur modules. And then he was finding that it looked a lot like Kirillov-Reshetikhin modules and so on. And then, so that's how they came to this. So they have 2 papers. I think one appeared in the Nagoya Journal and the other in Advances. And now more recently there are these papers of Naoi, N-A-O-I. So that's all on the web. And another paper, so by Kodera and Naoi. And they also say something about what Nakajima, so Nakajima always worked in the quantum case, but he had many results over there, and so they also say what it means in the classical case, I think. Yeah.
so this is a classic, like a classical
Mm-hmm.
translation into writing of your comments.
Mm-hmm.
Into credit.
Yeah, so then there's all this stuff with crystal bases and Kirillov-Reshetikhin modules and so on, but that's all, I don't know, there must be some papers of Schilling, and I'm not really such an expert in that subject, but I would think that if you're interested in the theory and these LS paths, then you should look at the papers of Naito and Sagaki. So they have various papers on the web, so you can. Yeah, and they're big on this Littleman path model. And I don't know if they do SMT, but they certainly do this Littleman path model and stuff like that.
Could you also say it's more on the work of Leffler, Hernandez, and
On these cluster algebras.
how it relates to Kirillov-Reshetikhin modules? There's some relation, right?
Yeah, but I don't know. Oh. I just have to say I don't know. Some of this might be there in this paper with Hernandez, in that survey, but no, I don't know cluster algebras. I'm not going to learn cluster algebras.
No, I don't know the need of that.
Yeah.
Just a statement because it can decrease of some.
Yeah. I'm not. I don't know either categorification or cluster algebra, so I think it's better if I don't say anything about it.
No, that's fine.
About AR modules themselves,
Yeah.
what are the kinds of things that people study beyond these crystal bases?
Then,
Algebraic and is there anything? If there are just specific examples of.
yeah, I think everything that is going. I think KR modules is a sort of exhausted subject, roughly.
So there's Q characters.
It's the minimal affinizations which would be more. There you don't know very much. You don't. I mean, you know their Q characters, but you don't know their G module decompositions if you're doing algebraically. So that is this one pair. So minimal affinizations.
There are modules, exhausted subject.
I would think so. Yeah. That's what I said. Yeah. I would say that the.
Can I write?
Maybe not.
Well
Yeah, I think well understood is a correct thing. I would.
Okay, so can I
Yeah.
write well understood?
I mean, all I can say is that even the people who do KR modules for a living are now wondering what, you know.
What next?
Yeah, so. I mean, there are still problems, like Schilling is still trying to write down crystal bases for E6 or E7, but they are sort of highly technical, and if you're not deep into crystals, then you're not deep into computers, so you can't make any headway there, I think. But I think,
Minimal affinization.
yeah, I think there, I mean, things are not so well known. So there are these so Hernandez has a paper on, I mean, more recently. So we wrote a series of papers in the 90s with Presley, but
Presley?
yeah. So where we sort of originally defined this. So I think there are 4 papers or something on this, 4 or 5 papers on this subject. So where we where we told, you know, what the Drinfeld polynomials are for the minimum. So we defined and said, but that classification is not complete. And so Hernandez has some results on the Q characters in the case where the classification is known. And Moore completed the classification for D4, I think. And he also has some results, I think, on their G module structure. In general, I mean, not just for D4.
So there is conjecture, I mean, I don't know if it's a conjecture on KR module. Was it about the Q characters, the thing that Hernandez?
So the conjecture on these Kirillov-Rashtikin modules was that the physicists have something called a Q system or T system or something, and then so this is like what Kleber would call the Jacobi-Trudy identities. For AN, if you take SOM, if you take 2 rectangular representations, right, in the tensor product, then you can write the Schur function as a product of two Schur functions again, plus some correction terms. So that's like the T system that these guys had, and what Hernandez proved was that. So this Japanese Okado and company had this conjectural formula, and they said if this rule held, then you can deduce G characters as well. And so Hernandez proved using Q characters that this was true. Actually, Hernandez, that's not correct. I shouldn't keep saying that. Nakajima first did it for ADE. And invariably what Hernandez did was to make it algebraic, and then he was able to do. But a lot of Hernandez's work is really coming from results that Nakajima first proved for ADE. I think these geometric versions are only quiver varieties and work nicely only in the simply laced case. So,
And this paper of Hernandez for the minimal affinizations is more recent.
yeah, that's 2007, something like that, yeah. So then there are some papers of, I don't know, Nazarov and Molev and so on, but where they study tensor products of minimal affinizations for just SLN. They would call them evaluation representations. If you weren't, but Molev, LEV, Nazarov. But their papers are very specialized to that case. And oh, and then they do it only for Yangians, I think. Yeah, I don't know. Yeah, Yangians. I think. Yeah.
Then we need something about current algebras. What you did this week.
What's his name? Savage and Senesi and people. They have a recent preprint on the web. Not Senesi. Kus and Kanda. One more paper. And there they do local wire modules for the twisted case, equivariant map algebras. But they have some restrictions. I mean, basically it's a twisted case for the current algebra. And after that, I think it's a straightforward modification of the case that they consider. So.
But this local wire module, so in your paper with Fourier and chemistry, that's the place where you have done it for the regions, right?
That's right, yeah. And that is in some sense the most, that is the approach that I really.
Okay. And this graded version of the graded thing is just, the modification.
Yeah, I mean, so Jacob and I had a couple of papers, and so that where we studied. So Jacob and I have about 3 papers on this current algebra stuff.
Okay. These more recent?
Yeah, well, but from 2007 onwards, I guess. Greenstein. You'll never find somebody called Jacob, so it's Greenstein.
So that's what I was wondering. Right.
It's Greenstein.
It's a precondition that if you do something there, your name must be simply,
I see, yeah. That's right, he's the odd one.
No,
Yeah.
I mean, he saved the day, otherwise your thing would have said.
BCG.
BCG proved it for 80
Yeah. Okay. So we have these 3 papers. One is called Current Algebras. So there that's the first time we start thinking about highest weight categories. So current algebra is something that appeared in. I don't know. Maybe that appeared in advances also. Anyway, so we have 3 papers there, and that's where all this graded stuff goes on. And then later in these 2. Yeah, and later just this BGG paper, I think, that we do too. Yeah. No, I don't think BCGM is actually graded.
Well, the morphs are generally not zero.
They're not, and the module, yeah, we're not worried about the graded case in that.
Okay, so
BCM.
BC. But there is also BCG.
The BCGM is about homomorphisms. So one of the results that I said yesterday, this W omega, W lambda injects into this tensor product. That's in BCGM. Yeah. So I mean, it's relevant. Yeah.
So this is BGT response.
Yeah. And BCGM is the homomorphisms between wild modules. That will appear, I guess, in representation theory.
Is that right? That or
Yeah.
is that right? Right. Okay. Maybe not again.
Thing that you mentioned about extensions, even between just for the low algebra finite dimensional representations, was that stuff?
That is there in one of these papers with Greenstein, the computation of X1.
For just F star A B.
Highest weight categories.
Yeah, so
Highest weight categories.
And highest weight categories.
yeah, so there are various papers which deal with extensions in the non-graded case. So Jacob and I have a fairly unreadable paper, but we do compute extensions for the loop algebra. And so extensions, yeah, so I guess extensions first appeared in a paper I wrote with Mura, where we computed the blocks of the category of finite dimensional representations.
So that result which you mentioned in your talk yesterday, it seems the G tensor, the homomorphisms.
Yeah, that appears actually in the paper with Greenstein.
This one that Matt just mentioned.
That's right, one of those papers, yeah. So that was for the loop algebra, and then this guy Codera did it for a G tensor A. And now Senesi and Savage and Nair did it for equivariant map algebras. And I think Yakelic and Mura did this similar thing for characteristic P, finding the blocks.
What is characteristic P?
So I mean, when these finite dimensional representations, you can consider the same category for working over modular representations. And you can ask all the same questions.
When you take the Z form.
You take the Z form of the loop algebra, you go to characteristic P. And look at finite dimensional representations there, and they did. Since we talked about this characteristic P lattices earlier, that's why I'm saying this.
Yeah.
And in the quantum case, I did, again, Mura and I did that for UQ, but I don't think. So let's see, Codera. So there are the various papers of Mukhin and Varchenko, where they sort of do current algebras and stuff. I mean, they're interested in Schubert cells and things like that, as well as. Anyway, so I don't know exactly what they do, but it might be something that more geometrically oriented people or analytically oriented people might be interested in.
And also you had the Varanulo Vasero. Yeah.
Yeah, they do those quiver varieties. Vasaro, Varagnulo, but I don't know what the reference. They're all quantum.
Oh, okay.
And yeah, so if you go to the quantum case and you want the geometric approach, then there's Nakajima, Vasaro, Varagnulo. Yeah.
Somebody else wants to bring up something that he's forgotten. I'm sure we forgot something, but does anyone recall?
I think there's you've written plenty for the moment.
Yeah. So let's again thank you.